Today, we'll go through the quick review of the digital modulation techniques. So now, the difference between digital and analog format itself uh, has some reason, because analog is continuous in nature. You cannot process or generate the continuous signals in real time, right? So you go for digital, where you go for discrete levels uh, in your output, and even along the time axis you make it discrete. So discretization along horizontal axis as well as the vertical axis results in the discrete waves now. So also we know the requirement of modulation. So the first basic requirement is that if you have a signal of lower frequency, it cannot travel for a longer distance, right? It faces interference, and the several effects of the channel will also deteriorate the signal's amplitude, so it cannot travel. So the solution is that you can uh, increase the range of communication, provided you increase the signal's frequency, right? So the original frequency content of the signal should not be altered. You can put the whole signal itself on another signal, right? You can perform the modulation. uh, this is true in case of continuous signal or the discrete signals. So continuous signals also, we have the phase modulation and phase or angle modulation, amplitude modulation, etc. Similar to that, we have amplitude modulation in case of the digital signal. We call it as a key, right? So amplitude shift keying, phase and frequency shift keying. So they are the equivalent, one on the continuous signal side and the keying on the other side, right? So now, what are the requirements? First, let's quickly go through the requirements of modulation, digital modulation. Now we are restricting to the digital only. Okay. Requirements of irrespective of what type of modulation we are using on the frequency side, on the digital side. So they have certain requirements, right? The first requirement is that you want to achieve the maximum possible data rate. This will be the first requirement always. Then, in order to achieve the highest possible data rate, what is the amount of power you are investing, right? So this should be minimum, correct? So the minimum amount of transmitted power is the second requirement. Then followed by, so there is what is called as the channel bandwidth. How much, what is the amount of message you can pass through a given channel, right? That is the width of the channel, right? So that should be right. It should be minimum. I have to keep the channel bandwidth, right, minimum for a given particular amount of message. In the sense, I should be able to send the message using minimum bandwidth, right? So that's why the third point becomes minimum channel bandwidth, right? Then what about the interference of the signals, right? Whenever there is an interference, there should be maximum amount of immunity, right, provided by the modulation technique, right? my original signal or the message signal should not get corrupted. This is what is expected, though practically that is not going to happen, but we can say that this can be a requirement, right? So this is the maximum amount of immunity, maximum immunity to the interferencing signals, right? Then, okay, right. So the one type of noise is something like because of the other signals that are present over the same channel during the same time, right? There are other versions of noise, right? Which is actually a noise source, right? That's a different type of noise. And there is also noise in the hardware, right? That's a different issue. Uh, all such issues we are not writing at this point. This point basically considers when you use a modulation technique, this modulation technique should not be affected by the other signals. That's all. Okay, not the noise of the channel, not the noise of the transmitter or receiver or antenna or something. Okay, right. Then okay, let's assume we achieved all of them, but definitely if you try to achieve all these points, your circuit will be very complex, correct? So hardware is going to be complex, plus complex hardware needs uh, a huge amount of the cost will be more, right? So we have to reduce that as well, correct? So this means we have to have two more points over here related to the complexity and cost. So minimum complexity of circuit, minimum circuit complexity, and you have to reduce the cost, so cost is also should be minimum, right? So also there is one more concept which is called as probability of error, right? So probability of error indicates when I send one, what is the chance that you receive zero on the other side, right? Or if you send zero from one side, what is the probability that you get the other sim, right? So initially we will look at only ones and zeros, but practically speaking you can actually send 2 bits, 4 bits, or 8 bits, 16 bits at together at once, like a symbol, right? So uh, just to understand the concept, we consider only zeros and ones. One bit is one symbol for us, okay? But practically there is a difference, right? So let me write that point as well. It should be minimum, right? Minimum probability of symbol error. These are our requirements. Now we will look directly go to the review of certain modulation techniques. Again, we are restricting to the binary. And if you remember, there are two types of communication possible in terms of modulation, right? So the again, we are writing the digital itself. So digital modulation can happen in two ways, that the ways are dependent on the type of carrier you are going to use, right? So the if the transmitter as well as receiver, they know what is the carrier frequency, right? Then the specific type of modulation used is called as the coherent, modulation. Okay, if at all the that information is not passed from the transmitter to receiver. In the sense, transmitter and receiver, they do not know each other, right? There is no communication, no clear communication saying that, okay, I'm sending the message with this carrier frequency, right? If it is not given, or if it is not designed in that way, this is called as non-coherent. So what's the requirement, right? So coherent means it is something like non-secured way, right? Because something is already known, right? So when you want to keep the messages in a very secret fashion, right, uh, preferably we are going to use non-coherent. The reason behind that is uh, the signal will be modulated, but at which frequency, which carrier frequency, that is unknown. So the receiver circuit becomes more complex, right? Because you need to add a circuit to identify the carrier frequency first, right? So you receive a signal on the other side, look at what is the carrier frequency first, identify that, then you do the regular demodulation process. Okay, so because of that, the non-coherent techniques are complex, circuits are complex, and that will definitely increase the cost as well. All right. Okay, so we'll move on to the first technique here. So first we'll look at the coherent uh, modulation techniques. Coherent, this is binary modulation techniques. So coherent ways of modulating and demodulating. If you are dealing with the amplitude, it is called as amplitude shift keying. Okay. If you are dealing with the frequency, it's called as FSK. Right. All are as of now it is under coherent ESK, coherent FSK, and we are going to look at the coherent PSK. Right. Three techniques we'll be discussing at first, right? Then we'll extend this concept further for non-coherent and various other techniques as well. Okay, right. So the first technique is this. So this is the coherent ASK. There is another name for ASK. Its amplitude is being changed as per the message signal, and we know that the message is either 1 or 0, correct? So when there is a message transmitted is 1, you have some amplitude. When the signal is 0, 0 means no signal. No signal means you don't have to send anything, so you turn off the transmitter. Okay, so since you are trying to turn on and turn off the transmitter, right, depending upon your message signal, so this is actually called as the on off key. There is another name like this. All right, now uh, for all the digital modulation techniques, we have a requirement of what is called as a basis function, right? The basis function will tell you where is the signal and what is the signal's constellation, right? Because always we try to plot the signal constellation to understand, right, the understand the position of the symbols, right? So for this reason we need the what you call as a basis function for ASK. Since you have only two amplitudes and one of the amplitude being 0, you require a single basis function. Okay, so only one basis function is required for ASK. That's something like an advantage of ASK. If you're using ASK, what could be the advantage? You need only one basis function. So the basis function uh, is, this is normally denoted as, say, phi of t. Since only one is there, I'll write it as phi 1 of t. For this ASK function, ASK modulation, I need the function defined as the 2 by TB under root. You can use cosine or sine, so we prefer cos function, cos of omega ct or 2 pi fct, right? This is there is a duration with this. You are not using the cosine function as it is. It's only between 0 less than or equal to t less than or equal to tb. Tb is the symbol duration. Okay, so here tb is the symbol, or it's a bit duration. Okay, as of now we are restricting ourselves to bits itself, right? One symbol is one bit, so general term is symbol duration. If one symbol consists of 4 different bits, then this tb is the duration of all the 4 bits together. How much time you take to send all the 4 bits, that's what is required. Okay, fine. So this is the basis function required. And what is the ASK waveform? Equation of the waveform, right? Equation of waveform is I can write it like the time domain equation. Equation of ASK wave. The wave which is generated by using ASK technique. This is S of t is equal to, this is root of EB times phi 1 of t, because root EB is the energy content in that symbol 1. So symbol 1 has energy root EB, right? Symbol 0 has 0 energy. So 0 into phi 1 gives you a 0. So S of t becomes either root EB or 0 dependent upon what you are sending. See, this is the amplitude part, right? Amplitude, I am going to put it over a message, over a frequency signal, so carrier frequency. Okay, so it is very much similar to the amplitude modulation in the continuous waveform modulation techniques, right? So this becomes equal to, now, so the root EB I'll multiply to the above equation to get 2 EB by TB under the square root into cos of 2 pi fct. So again, we know that there is a condition saying that 0 less than t less than equal to tb. Right, now we'll write the constellation as well. So before writing the constellation, so when I'm trying to send the signal, let us say the signal is 0. If the signal is 0, that means symbol 0 is being sent, right? So we'll write, therefore if I'm trying to send the symbol 0, this corresponds to the signal. There is no signal, correct? Signal is 0. So signal is 0 indicates that, let me define the point, that is S2 on my graph, because S1 I already have defined as the root EB. Okay, so signal is S2 equal to 0. There is no signal. For 0, I call it as S2. So if at all you are sending symbol 1, right? What is the signal you are sending? Signal is S of t is equal to root of EB times phi 1 of t. This means, right, the coordinates of S1 is root EB, right, in one-dimensional space. So let's try to plot this. On this axis, it is phi 1, and I don't need any other axis actually. Okay, so let me mark a point over here. This is the root of EB, and I'll write a 0 over here. Okay, so let us say this is corresponding to 0. This is something like origin. Now, what is the central point? That is the decision boundary, right? So it is midway from 0 to EB. So what is this point? This is the root of EB by 2. right? So I can call this as S, I think S2, I mistake. So 0 is a S2, symbol 2 is 0, symbol 1 is 1, correct? Now we understand that anything that comes on the right side of this will be, it's actually on the receiver side. Okay, so on the receiver side, if you get any point which is right side of that, it's called it will be classified as symbol 1, right? And anything that comes on this side, you will call it as symbol 0, right? So though you sent this, because of the uh, something like maybe the noise or imperfections during the communication, this point might get shifted until this, right? No problem, that's okay, it will be classified. But if it crosses to the other side, then there is a problem. The 0 symbol will be classified as symbol number 1, okay, and vice versa. So this is a region. Let's denote the region as Z0. This side is, say, a region Z1. Okay, so this is the constellation diagram required for ASK, right? And then let's quickly go through the modulation. uh, let's see. Okay, the something like a block diagram, ASK modulator, how the ASK modulator looks like. Right, normally we have the message signal that is considered as zeros and ones will be the input, right? So again, we are considering the easiest format of binary data. Actually, if you remember, the binary data can be represented in several formats, right? Something like you can have return to zero, non-return to zero, polar, bipolar, etc. Many things, right? In many way, the zeros or ones can be actually represented in several of the ways, right? Whatever we know, right? Out of which we are considering the easiest one, which is non-return to zero binary, right? It means it is unipolar. Only one pole is there, polarity is there. Either you have something positive or zero. It's not coming to zero somewhere in the middle. So non-return to zero binary data format is the form in which the data comes to the modulator. The original message signal comes in that format. Okay, this is what is assumed. Again, you can definitely consider other forms as well. So what is the change when you change the format? Your power spectral density, the power distribution of different frequencies will change. Okay, because of that, your frequency spectrum will change, right? So those things, right, will internally those modifications will happen, because if you have the rectangular pulses of different widths, we know that on the frequency side we have different variation in terms of the frequency, right? So a larger width pulse has lesser frequency on the other side, whereas the shorter pulse has more frequencies, right? Because of that, you see now non-return to zero and return to zero will have difference in terms of the width, correct? So because of that, you have variation in the frequencies. So let's try to keep it as simple as possible, right? So we are going to consider the non-return to zero. This is NRZ binary data, indicates that I am sending either 0 or root EB only, right? In the somewhere in the middle, signal is not going to come to 0. This is my message signal. We are giving this message signal to a product modulator, right? The product modulator will simply multiply the incoming signal with the phi 1 of t. So that phi 1 of t is the root of 2 by tb into cos of 2 by fct. Right. So what is this? This is the PM. I'll write PM, indicating that it's a product modulator. Directly, it generates the S of t. Correct. So S of t is could be one of them, like 2 EB by TB under square root into cos 2 pi FCT. Otherwise, this could be 0. Okay. So when this is, it's 1 whenever if 1 is sent. So this is if 0 is sent. Okay, now dependent upon, see, this looks like a bandpass signal, right? So I'm actually sending only a specific frequency centered at a frequency FC. Around the FC, you are sending something, right? So in general, the if SB is the band pass signal, right? If this S of T is band pass, so I'll make one point very clear. So S of T, whatever we are sending, is a band pass signal. And for any bandpass signal, we try to write its power spectral density, right, in the following notation, right? So if this has S of T has a power spectral density SB of F, okay? So let's say S of T, I'll write an arrow mark to calculate the power spectral density. Let's denote this as, it's actually what do you mean by PSD? PSD gives you, it's a plot. That plot gives you an idea that in S of T, on the frequency domain, at what frequency, how much power you are sending. Okay, like 2 hertz, 10 watts. At 20 hertz, you are sending say 200 watts, and so on, right? Okay, so this is denoted as SB of F. So the B indicates that it is a baseband. uh, you are actually looking at the original signal in its most pure format, okay, purest format. So this is the baseband PSD, okay, baseband signal which occurs in naturally. S of T occurs naturally, let's assume. Okay, so if this is the SB of F. Now what is the SB of F we are looking for a ASK, right? For ASK, this SB of, we have actually a derivation for this. Since we are just reviewing the concept, I'll skip the derivation part. Okay, the SB of F could be in the following format. So a square by 4 times, this is delta of F, plus this is a square TB by 4 sinc square of F times TB. All right, so here A is a constant, that is root of 2EB by TB. Okay, so now we can understand something, few topics, few points from this equation, right? There is a delta function coming up in the PSD, and also there is a sinc square coming up in the PSD. Can you tell me why? It can be guessed easily, right? Can you guess the reason why we have a delta function and why do you have the sinc square function? So here you can see that the delta F comes into picture because of the presence of cosine function, right? Because cos has, when you take the cos functions Fourier, right, it gives you F minus FC, F plus FC, delta function, right? Anyway, that's the original Fourier transform. But since we are not looking at the Fourier transform here, and since we are looking at the power spectral density, right, we get a delta of F. Okay, that's the first thing. And second thing, the sinc function comes into picture because, right, we have rectangular functions that is present on the time domain, right? How, where's the rectangular function in this? Because we don't see a rectangular function in the equation of our S of T. S of T is showing something like only either you have a root of 2EB by TB cos function, or otherwise 0. But you see, actually, when the signal is there, you are sending something. When the signal is not there, you're not sending something. So only this shape is modified. You have cos function, then 0. Once again, cos function and 0. You see that there is a rectangular wave which is actually, right, getting modulated. So that rectangular function has a Fourier representation, sinc function. Rectangular Fourier transform is a sinc. So since you are trying to get its power spectral, there is a sinc square function coming in the picture. Right. So those 2 points are important. We will be able to identify what is the time domain signal by looking at the PSD itself. This is one technique. Okay. Anyway, so if this is SB of F for the given ASK, then we can prove that, right? The SS of F, which is the actually the total, what you call PSD, right? So this is actually the baseband PSD. Then the total, I can write total PSD is given by, this is denoted as SS of F is equal to 1 by 4 times. This is SB of F minus FC plus SB of F plus FC. So this is the equation, right? Using which you can calculate the total power spectral density of our signal, that is ASK. Now let's look at, see, the frequency domain view is not required. Actually, we are dealing with a binary signal wherein the power distribution is very important for us. Okay, right. So before that, let's draw the time domain view of the signal. That gives you a very clear idea. Let me assume that I am trying to send the following symbols. Okay, let me write in the following fashion. So okay, this is the time axis, and I want to send the symbols such as, say, 1, 0, 0, 1, 0, 1. Okay, if I want to send some symbols like this, let me divide the space into, sorry, let me divide this space into equal symbol durations first. So once I have the symbol duration which is defined, I can definitely use those symbols, and right, I can use those symbol durations for creation of various the waveforms. Okay, so this is how, let me assume that this is how I divide. So this is the symbol duration of 1. So then let me assume that this is the symbol required for zeros, and all right. So this is how the symbols are allocated with the durations. So this is the time axis, that is t. Now, if the amplitudes are supposed to be limited to the maximum and minimum value, like this, because you have, it's a cost function, right? Cost function has a upper limit as 1, lower limit as -1, or any other value. It depends on the EB now. So this is how the binary data looks like. Okay, whenever you are sending 1, right, you will see a wave like this. Whenever there is 0, you are not going to see anything. So once again, you have 1. So you have this, right? And 0 means no wave. Once again, I have a 1 here. So you see. So 0 indicates you are not sending anything. That's why this region is 0. Okay. Again, here there is no symbol being transmitted. That's why this is also 0. Okay, so you can see that symbol becomes 0 over here, right? I am not sending anything, so the amplitude becomes equal to, this is ESK waveform in time domain, right? Now you see the rectangular, function that comes into picture is just because of the following. It's because we can see that, see, this is the rect function. I can see the rect function at various other points. You can see that, right? This is how it looks like. So because of this, the sync square comes into picture. So there is a rectangular wave plus there is a sine or cosine wave. So both will generate you the delta function plus the rectangular will generate a sync function. That's why you can see that our power spectral density of the baseband function, it has the two components. One has a delta function and one more component has the sync square. Okay, now if you look at this, the plot of this SS of F, that is a power spectral density. This is what is important. Okay, so let's try to plot that. So this is the PSD power, total PSD. Okay, PSD of ASK. Right. So the PSD of ASK looks like this. Okay, let's assume that this is the frequency axis now, because we are looking at the power spectral density. So along the y-axis, we are trying to plot SS of F, right? So we are sending the signals, in the sense we are modulating the given binary signals of zeros and ones of energies 0 and root EB around a specific frequency FC, right? And we saw that the FC part, exactly at FC, I have a delta function coming into picture. So I will denote that delta function like this. So it's like I have a delta function that is, we are going to see a delta function at FC. So this is that delta function. Okay, at FC and at minus FC, we are going to see that. Okay, so this is right. Okay, so this is these are the two delta functions. Okay, assuming that they're placed at equal distance from zero. Okay, I think somewhere here maybe. Okay, right. So I'll denote them in the following fashion. So this is 0 hertz, this is FC, this is minus FC. Now, what should be the amplitude? The amplitudes are, you can see that it is actually square terms. So you have the square of whatever it was in the original format. You have a square by a by 4 was there, so this becomes a square by 16 into the delta function. So delta of f, right? Okay, I cannot write the delta here. So magnitude is delta of a square by 16, but their positions are determined by the delta function's position. This could be something like this location is a square by 16 into delta of f minus fc. Okay, so on the left hand side I have a square by 16 into delta of f plus fc. Okay, so anyway, I just marked the magnitude, that is a square by 16. Then let us assume that there is a sync function. So what is the width of the sync function? It is infinite. It's going from minus infinity to plus infinity. So we cannot plot the sync function completely. That's the first thing. Okay, but definitely we can, there are some lobes present, right, for the sync function. Few of them we can definitely draw. Okay, so I'll mark some points here. So this is one. Okay, I'll give some more space. Let me assume I'll mark 2 points on both sides. One here, one here, one here, and one here. Similarly, for the negative side, negative frequencies as well, let me plot one or two points on both sides. Okay, so okay, let me assume that this is the highest peak that the sync function can attain, and let me denote that point as, once again, a square by 16 into the TB. Okay, when you multiply by TB, it reduces, so TB is actually lesser than 1, right? So that's why. Okay, now the sync function, let me change the color. So it actually starts from the peak, it attains a minimum value here, it goes to a peak, and once again it's going to attain another minimum here, and so on. It actually goes till infinity. Similarly, on the other side, it comes from the top, attains a minimum value, goes to the peak, and once again comes down, and once again it goes till infinity. All right, the same thing is repeated on the other side. So this is how it should look like. Okay, copying the same thing on the other side, and so on. Okay, now let's try to write the values at which the function reaches minimum, right? So this is, it's a f, whatever is the frequency, fc plus 1 by t. Okay, this position is fc plus 2 by tb, and so on. The next position will be fc plus 3 by tb, and so on. So this should be fc minus 1 by tb. Okay, this is fc minus 2 by tb, and so on. I get minima coming up at fc minus 3 by tb minus 4 by tb, and so on. Right. Similarly, on the other side, minus fc, I have minus fc plus 1 by tb minus fc plus 2 by tb. On the other side, I have minus fc minus 1 by tb. Next point will be minus fc minus 2 by tb, and so on. So the amplitude of the sync wave is a square by 16 times tb, right, into sync square, right? So I'll write the waveform as well. So this, it has an equation like this. This is a square by 16 times tb into, this is a sync square function. Okay, sync square of I think f minus fc should come because it is shifted to right, f minus fc times tb. This is the equation. Okay, so what we have on the left side has an equation like a square by 16 tb into sync square of f plus fc. Okay, so this is all about the modulation technique, how the modulated signal can be obtained from simple baseband binary signal, right, using the ASK. Right. Now, let's go for the demodulation technique. Again, there are multiple ways in which you can perform the demodulation, but we'll stick to the simplest ones. Okay. So, the demodulation again happens with the coherent way of detection. So you see the coherent modulation, the word comes not because of the modulation techniques, it is because of the demodulation techniques. The demodulator knows what is the frequency. Okay. So, this is the coherent detection. Coherent detection of ASK. Right. So coherent detection, as the name suggests, you know what is the frequency of the carrier. Correct. So let's directly write a block diagram. Block diagram itself is sufficient to understand the whole concept. Okay. So let's try to write a block diagram now. So let us assume that there is an antenna. Okay. This antenna basically picks up the signal which is coming from space. So I'll write it like this. What you are receiving is the ASK signal. Okay. So this is the ASK waveform that is received by the antenna. So let's denote that as x of t. Okay. So ASK signal that is received here is x of t. Okay, so when this x of t is picked up by the antenna, right? Inside the antenna, inside the circuit, you have one more product modulator, right? One product modulator we already have seen was present inside the modulator circuit. Now it is a demodulator circuit, and since this demodulator or the receiver knows the frequency of carrier, it directly generates that and keeps it ready. So the phi 1 of t is available here as well because it knows, right? So 2 by tb under root, see the cos function is already generated, cos of 2 pi fct, because fc is known to you means you can definitely generate this. Okay, once this is done, next part you have a simple integrator circuit. It performs integration 0 to the t dt. So integration is carried out and then you sample it out. The next part of the circuit is a sampler, right? So we denote the sampler in this fashion, like this. So this is going to take the sample. This is going to touch here, right, at every TB, at each TB, right? So once from between 0 to TB, it will touch once. So then TB to 2 TB, it will touch once again. Like that, every TB duration, it will touch. Okay, so once it's every time it touches, it gets a value over here that is denoted as x1, right? The value of the sample is x1. Now what happens? Here I have a circuit to make the decision. In the sense whether 0 was sent or 1 was sent should be decided based on this x1 itself, correct? So this x1 enters into the decision circuit. So normally in the most simplified fashion, decisions can be taken based on the thresholds, right? So let's denote the threshold over here. So there is a predefined value of threshold. So what is the V threshold? It's in terms of voltage only, because we are dealing with the circuit. So circuits are working based on currents or voltages, right? So if you go back and check the constellation of this, so the constellation says that the midpoint, the halfway through your 0 and root EB is the decision threshold, correct? So root of the EB by 2 will be kept as the threshold, right? So now the x1 is compared with this V threshold to make a decision, right? So this is the output, and here we write what could be the decision, right? So here the decision taken is a symbol symbol 1, right? For all the values x1 greater than V threshold. Okay, so symbol 0 will be the decision made if the x1 is less than V threshold. Okay, so normally the greater than or equal to will be assigned to the symbol 1. Okay, less than is assigned to symbol 0. Maybe there are some variations depending upon the depending upon how the design is made. Okay, so if the x1 is more than V threshold or equal to V threshold, it's one symbol 1, right? Otherwise symbol 0. Okay, then corresponding to any of the modulation technique, we have to have an equation for the probability of error. Okay, so that's the last point corresponding to ASK. So probability of error, this basically indicates when one of the symbol is sent, what is the probability of the other symbol being received. Okay, so in this case, again we actually have a longer derivation for probability of error calculation. So we'll skip that. We'll directly write the equation. Okay, so probability of error, PE, is equal to half of ER, the standard ERFC. Okay, standard error function of half of root of EB by N naught is the equation for the calculation of the error function. That's the probability of error for ASQ. Okay, so the N naught by 2, here the N naught is defined, so where the N naught by 2 is nothing but the variance of the noise. Why the noise is considered? Because uh, whenever we are considering the communication channel, 1 becomes a 0 or 0 becomes 1 only in presence of noise. So there has to be a noise. Okay, so we use that noise, and whenever there is such noise, again during the derivation we will be considering the Gaussian distribution for noise. Okay, Gaussian distribution has zero mean and n naught by 2 as the variance, so that's why. So I'll just write here the Gaussian. Okay, right, so the EB by n naught is the, yes, SNR of, right, the symbols. Yeah, this is all about the amplitude shift keying, right? So we'll move on to the coherent binary phase shift keying, PSK, in the next class.